So in class, we have previously discussed about an inversion of the slider crank mechanism, where we have a crank, a coupler, and then the sliding block is right on top of this. And it is not just at an offset, but it is on a link which can rotate. This is like a weld, which means that there is no way for instance, this slider cannot become turned like this by itself. So this state of the slider is not possible, which means the sliding axis and the output link are at a fixed angle. This angle, we called it gamma. This was theta 4. I'm going to call it gamma prime because that's a different weldment. And then the crank would, the coupler would have to go through this. Then possibly something like this would be the linkage. There's a pivot, there's a revolute joint there. So these are two different, this is one geometry, this is another geometry. These two cannot be obtained from the same geometry because this is a different weld angle. And we studied the position analysis of this, and we said if we look at the uh, angle theta 3, it is over here like this, and we said theta 3 is equal to gamma plus theta 4, and that gave us a relationship which was required to solve the equations for the unknowns. We also saw in the case of velocity of slip, we revisited this mechanism, and we talked about in the analytical method how if we describe the loop closure as e to the ij theta 2, a e to the ij theta 2, this is second, this is third, and this is fourth link, this is the first link. We can write the loop closure as this. And then we can take a derivative and we get j a omega 2 e j theta 2 jb omega 3 e j theta 3. We get an additional term b dot e j theta 3 and jc omega 4 e j theta 4 equals 0. So we got this term which was describing the velocity of this point as it moves away or closer to this point. So the b length was changing, and we said we need three equations to solve for various unknowns, and then we used the idea that theta 3 is gamma plus theta 4, so omega 3 should be equal to omega 4. Similarly, taking it one step further for acceleration analysis, we take the derivatives, we will also realize that alpha 3 is equal to alpha 4. So essentially, the rotation of link 3 and link 4 are coupled to each other. So how much ever is the rotational velocity of 3, we get the same angular velocity of 4, and the angular acceleration of 3 is same as the angular acceleration of 4 because these two are jointed using a prismatic member here. There is also in the acceleration, there is a component of Coriolis acceleration. So let's write the uh, acceleration equation. This should be square j theta 2 plus j a alpha 2 e j theta 2 minus j square b omega 3 square ej theta 3 minus 2jb dot omega 3 ej theta 3 minus b double dot ej theta 3 minus jc alpha 4 ej theta 4 minus jc j square c omega 4 square ej theta 4 is 0. So this component here is the Coriolis component, which will exist in this case. This is the slip acceleration. This is the centripetal acceleration, another centripetal acceleration, another centripetal acceleration. This is the tangential acceleration, and this is the tangential acceleration. I believe I missed a term. There should be a j b alpha 3 e j theta 3. That would be the tangential acceleration of link uh, B, or point B in link 3. So for the force analysis of this mechanism, we will consider uh, say a body like this is the crank. There is a link here, and then there's a sliding or there's a coupler link on which there is a sliding block. And then that sliding block has a center of rotation at O4. So here we have pivots, and then we have through position, velocity, and acceleration analysis, we have already obtained what are the different angles at which these are at the state. We have alpha 2 and omega 2 of the crank, and we can start looking at the free body diagrams of each of these and consider what are the forces which are acting on various either at joints or um, external forces acting on the body. So for the purpose of this analysis, we will consider the sliding joint to be frictionless. We have obtained the angle theta 3, theta 4 from position analysis. We also know omega 4 and alpha 4. We have the crank. We know there will be a joint reaction. So this is, let's say this is O2, A, B, and O4. At O2, we know there is a joint force of the type 2 on 1, and corresponding to that, we have 1 on 2, which is, say, this will be equal to minus F12. Then we can identify the CG of the link. The CG of this link is, let's say, somewhere here. And at that CG, we will know the acceleration of this body. Let's say the acceleration is something like this. And then we have force of the joint here of the form F3 on 2. We can identify the positions of these in either a local rotating or non-rotating coordinate system as per our convenience. I'm just going to use a local non-rotating coordinate system at the CG. So if this is if x and y, we have a position like this, which is R3, 2, and we have a position like this, which is R1, 2. We can consider there is a torque T1, 2, which keeps everything in equilibrium, in a dynamic equilibrium, and that these will all be the forces of the crank. We can consider the coupler next. So let's say this is the coupler link. with CG at some point like this, and at CG we will see there's an acceleration something like this, AG3. Of course, there is a force which is in this direction here, 2 on 3, which is equal to minus F32. There is going to be a force um, along the axis of slip, or along the axis of transmission, and say if the at this given instant the link length is B, then the force will be acting at this point and be perpendicular to the link length. This will be F4 on 3, which will have a corresponding force on link 4. Let's draw this way. Then I'll have a force here, which is in this direction. This is F3 on 4, which is equal to minus F4 on 3. From CG, this distance is going to be R4, 3, and then this distance is going to be R2, 3. We know the acceleration alpha 3, and we know that this this is the axis of slip. We can write a unit vector along this direction. For instance, we can say U hat is along the link. That would be the axis of slip. And the force F3 has to be perpendicular to that axis. So the remaining one is link 4. We can consider a CG, let's say at this point. There will be an acceleration AG4. There will be a force 1 on 4. Corresponding to that, there will be an equal and opposite F4 on 1. This should be equal to minus 1, 4. And we can consider that this joint reaction or this force F34 that is acting on the slider, although this will be distributed along the length of the block, which is in this current situation unknown, we can, for the purpose of this analysis, consider it to be acting at this point, which is at the center. This is where point B is of the slider block. And so there will be a position R3, 4 of this point B at which F34 is acting. We know there is an acceleration alpha 4 for this link. There is also this position R14. Note that R34 and F34 don't have to be along each other. If there is a certain tilt depending on the gamma value, then F34 will be perpendicular to the axis of slip, whereas R34 will just be connecting this point to this, which doesn't have to be perpendicular to the axis of slip. Say, for instance, if the slider block is made in such a way that the CG happens to be here, then R34 will be along this line. Now I'll start writing the equations. Here we know we can get F12x, F plus F32x is equal to MAG2x. We get F12y plus M32y equal to MAG2y, and we can write the torque equation T12 plus R12 cross F12 plus R32 cross F32 is equal to IG2 alpha 2. And similarly for the um, coupler, we will have equations F 43x minus F32x, just like how we wrote for the slider crank without the rotating fourth link. This is a similar equation. So this was M2 here, M3 AG3x. We have 43y minus 32y is M3AG3y, and then R43 crossed with F43 minus R23 crossed with F32 should be equal to IG3 alpha 3. In this case, we can identify an additional relationship and say that F43 is always going to be perpendicular to the axis of slip. So F43 dotted with U, or U dotted with F43, is always equal to 0. You can expand this to write U in the x direction times F43x plus U in the y direction times F43y is equal to 0. And we already know that because this U is along the axis of slip, you can directly write the vector components of U as cos of theta 3 and Uy as sine of theta 3. In addition, now we have for this F34 or minus 43x plus 14x is M4AG4x minus 43y plus 14y is M4AG4y, and you have R14 crossed with F14 minus R34 crossed with F43 is equal to IG4 alpha 4. So you got 10 equations. These are 3, 3, and 3 for the links, and an additional equation which ensures that F43's direction is orthogonal to the axis of slip. So we have 10 equations, but you only have 9 unknowns, which are 1 to x, 1 to y, 3 to x, 3 to y, 4 3x, 4 3y, 1 4x, 1 4y, and t12. These are only 9 unknowns. So one of the equations is redundant. So what we can do is take this equation, the torque equation for link 3, and we can take the torque equation for link 4, and we can write one in a combined form, because we know alpha 3 is equal to alpha 4. We can add these two and write R43 crossed with F43 minus R23 crossed with F32 plus R14 crossed with F14 minus R34 crossed with F43 is equal to Ig3 plus Ig4 times alpha 4. Thus, we have 9 equations and 9 unknowns, and we can put these in a matrix form and solve it to obtain the unknown quantities.